That's great. We're at half past, so we'll start off with the next speaker. I want to particularly thank Sasha here for stepping in at the last minute. We had a speaker who was unable to reach Brussels due to some travel issues. And so on 2 days' notice, I'm very, very happy that we have this talk. And I'll let you mostly introduce yourself and the space operations facility at Aachen. Thank you.
Yes. Thank you very much. Thank you also very much for getting the opportunity to having this talk. Actually, we should have this talk 2 people, but my co-mate decided to drive by car because he was not at Aachen and the car got broke. So I have also now to present his faults, but we will make the best. So we are I come from Aachen University, and I set up there with most scholars and bachelor students a ground station that aims to be like a multi-purpose ground station. So most of the operations we perform is with ham-based satellite. My first access was not in the space industry or so. I'm a chemist, and in a little project with this pocket tube you see there, my best friend, who was an informatic guy, wanted to develop this satellite, and then he asked me if I could a little bit help with managing all the stuff between the launch provider based in Italy and our little 3-man group. And then later I became then responsible for setting up a ground station with basically no knowledge at all. So it was really try to do something in the best with it. And then we had a somewhat successful mission, the RAN mission, with this first pocket tube, which was a 1-unit pocket tube at that time, back in 2013. Later on, because for that mission we had no funding at all. We had a little bit crowdfunding money, but we had everything got into the development and into the launch. So, but we still needed to test this little satellite, and so we asked many people, and one of those people were the University of FH Aachen, and they said, well, okay, since you're the guy, since you are also setting up a ground station, we have a mission, the Compass 2 mission, so we make for you the acceptance test, and you will help us to set up the ground station. And then, although at that time without no knowledge, just said, okay, let's do it. And then we did it. And now 8 years after that, no, 5 years after, we have now this team consisting about 21 students. First, we began with 7 students. Most of them were freshmen, so also they had no knowledge at all. So they had some ambition to learn something about space technology and maybe one day get into space operations, being space operator, something like that. And then came this Compass 2 mission, but the satellite never worked, but we trained a lot. And then we decided, okay, now we have the equipment, we have software, most of it open source software. What now? Well, let's do a ground station for others that maybe have the same problem and can find their satellite and so on. Okay, so a little bit about the equipment of the space operations facility. So since we have practically no funding at all, we make everything with a lot of creative engagement and by ourselves. So we have a wonderful Yagi array. It's for the 70 centimeter, it's 4 clockwise polarized, 18 crossed Yagi elements. Then we have also for the 2 meter, we have an array of 2 of those antennas. We have helix antennas, quadrifilar antennas, Lindenblatt antennas, mostly done, as you can see, by our own efforts. Then later we get the opportunity from a high frequency institute to get full access over the intranet to their antenna dish, which is a 3 meter dish with a log periodic feed. And we operated with an RTL SDR, that was the first one. And later on, they get us the access to a Rohde and Schwarz EM100 SDR. So here you see again some stuff going on. Since we are located in Aachen, it's a really rainy city with a lot of wind going there, so we constantly have to make maintenance. Okay, our radio equipment. So of course we started basically with this one. I don't know how much it costs. It's still between 50 euros and 80 euros. And with the old equipment from a mission long time ago. And which is an ICOM 910, which we use for all the satellite communications that are amateur radio based. But we not only perform communication with satellite in the amateur radio band, for example, do we also track weather satellites. And so the ICOM cannot do this because it's below 2 meters. And for those, we are very, very happy to use these RTL dongles. And now, so it's not true that we get not funded at all. So we got some money from the institute, which then regarded, oh, there's something going on here with these students, and so let's fund them a little bit. And so now we have this week just it arrived a new ICOM 9700, which can be completely operated over LAN, and we are very happy about this because our room is located on the 2nd floor, so we have very long cable pathways, and which really sucks the radio signal. And in one mission we realized that, I will come later, and so we decided, okay, let's bring everything on top of the roof and then operate everything completely remote. Okay, also this teleport is already remoted somehow. Here for this EM100, for example, one capability, we tried once to make a moon reflection from Belgium to the moon and then to us at a distance at that time that was in 2018 of about 800,000 kilometers. And you can clearly see here this peak here. What we also do, we work a lot, and we are very, very grateful about this with ESA operations. So sometimes we shadow track together with them the cluster satellites. Here, for example, you can really see the cluster satellite that's like a cylinder with one antenna, and it's spin stabilized. So here you can really see the rotation, and you can easily calculate at which rate it rotates. When we are in communication with other teams, for example the ESA, or with other ham radio stations for which we try to get signals from their satellite, or also sometimes do uplink, we use Mumble as a communication tool. Yes. So, and that is then, and this is our main room. And actually with a really good computer, you could operate all of those software with only one computer. But since we have really old machines, we delocalized every task on different machines. And so that's why we wrote software that transports the protocols, for example, to talk with the HDSDR by the net using the Orbitron propagator. But I have some diagrams for this. Okay, so since we said, okay, we want to be a multi-mission ground station, so we use a lot of different software, different tools, in order to be able to make use of all the protocols needed. And we are also beginning to implement CCSDS. That's why we work strongly together with ESA. They help us a little bit in order to get things done. We use tool and elements, and now also the CCSDS OEM protocol. Okay, so in this really short time we operate this station, we operated, so when I say operate, that's by mean of uplinking to the satellite in order to command the satellite. We have a good cooperation with Japan. Now ongoing, here we track ESA OPSAT, but we are also experimenter on that satellite. It's a satellite that allows you to upload an experiment, and then you can somehow play with that experiment. And okay, ESA cluster, this was just this shadow tracking. And this is all done with students that are in the age between 18 to maybe 22, 23. And yeah, so which performs their bachelor thesis at the end. So here you see when there's a lot of action going on, since we have 3 teleports, we can really operate all antenna at once. And so you need a lot of people. You can track a weather satellite and also get the signal from their Argos beacon. At the same time, maybe there is the ISS passing, and you make some digipeating with that one. So all this is possible. And in order to get the things a little bit structured, since there are 21 people, and we really want to train them to think and to act as an operator, we have also a certification process with a recycling process, so that every of them have to perform a minimum of passes per quarter in the year, and then they get a certification, and if they do a little bit more, they get an instructor certification, so that those guys can then instruct the younger generation and so on. So we try to overcome this problem that you always have in universities. As a university teacher, you have a fine group of 5 people that are really brilliant, and then they are finished with their studies, and then it dies completely. So with that, we try a little bit to get a continuity in this thing. This is basically not really my fault, so I try to read a little bit, but yeah, I can understand. So basically, the operation starts always with a predictor, and then through some different protocols, for example, for Orbitron that we use extensively, which has this MyDDE wrapper. Then we go to the different computers for decoding and for antenna control, which routes then to the actual device, which is for the rotor control, that's basically just a motor that points the antenna, or a so-called cat box, which gives the frequency needed to the ICOM receiver or transmitter. Since you have to follow the frequency, because satellites are satellite signals are subjected to Doppler shift, so you really have to follow this. And this basically for all the teleports that we have. So we have 2 teleports with rotors and 1 teleport just with omnidirectional antenna, quadrifilar antenna. So here you don't need the rotor, but you still need to follow the Doppler shift. So here's a little bit more concrete. So this is the propagator, which calculates the position of the satellite from your point of view, and then it transmits that with this little application, and from there we design 2 applications that then transfer those coordinates and the frequencies to the different rigs, but not directly, because we use HEMLIP as a layer in between. The HEMLIP is running on a Linux machine, and that is also something we had to learn really painfully, because since we are in a university, in the structure of the university, and they make all the time updates, and you come on one day and then you see yourself, your software not working anymore. And so we decided, okay, let's do it in a virtual machine. So at least we have a little bit of room left for changes by the IT. So, and then from there it goes then really to the desired hardware. For the demodulation and decoding, we use for the moment several modems, mostly written from amateur radio guys. RGB packet engine, some older stuff. For example, we use FLDigi. There is a Spanish satellite, FHASOF, which is a really tiny satellite, where we use FLDigi to, better say, we try to use FLDigi, because we didn't get a decode of that satellite still. Now really new, so GNU Radio is very new to us. So for us it's still experimental. So this will be the new implementation that is being installed, but maybe because of a lack of knowledge, we are still not able to use it fully. Because so what we aim what we always try is not to just record the signal and then try to decode it afterwards. So we always try to get it decoded as the pass happens, and it works most of the time. But then I have the problem also that the student, when he has his pass to perform, then he prefers to use the stuff he knows, because he can set that up without really reading the procedure within 10 minutes. And it's really complicating then to implement, also to younger people, to implement new stuff like GNU Radio. So, but we are working hard on it to get that done. So here again, so this is then the application that gets from the propagator, for example, here there's the frequency stuff. Then this is the SDR radio. Then we have a freeware virtual cable from where we get the audio part of the signal, and then we route that to the modem, and that makes then a connection to a terminal where the information is then stored as a hex dump, and after then you can load that information and get data that makes sense to the human. Sometimes it's not so complicating. For example, you have also satellites that all have implemented all this, so you maybe don't need the decoder, because the modem, because it has the modem already built in. So here is one of our first experiments. with GNU Radio. Here we try to get it run for OPSAT, but what we really want to do is we want to use this one because we have now a new problem that came up. Since 1 year ago with RTL dongle, we really could easily receive signals in the 70 centimeter band, but now it's so totally full of stuff in there that often. So here was the beacon of OPSAT, but then came this big, disturbing digital signal. I don't know what it is, and then you can get any decodes. But when we use the ICAM, the conventional transceiver, we can get it very well. For example, using SDR, and this GNU radio application uses directly the SDR. We were able to get it for a really good path, because there are good passes and there are not so good passes. The good pass is often a pass with a high elevation. We get 5 packets, and if you use the ICAM without anything, for a very, very, very bad pass, we get at least 33 packets. So, and that is really a problem. So we really hope that we can get the IF of this new ICAM, get it work and connect it into the GNU radio, so that we can really use the full power of the system. So that is for the moment, let's say the cheap setup that we use for that, as I explained it already. Here you see that was with the ICAM, lots of packets for a pass with an elevation of below 30 degrees. What still really works well with the cheap SDR radio dongle is a weather satellite on the sub 2 meter band, because that's obviously not in the amateur radio band anymore. It's below of that 2 meter amateur radio band. So here, even if it's a low elevation, because we have this strong antenna, we really can get weather satellite images from one horizon to the other horizon. So it starts at about 3 degree to 4 degree elevation, right then to the other 3 to 4 degree. So we get really an image from, you have parts of Africa, and you can also have parts of the Greenland ice sheets all in one image, which is really awesome. So for the uplinking, it's a little bit the same thing. For the moment, we use this easy term, and then we go again via sound modem, and we hope that also here one day we will be able to fully use GNU radio, because we really want to get rid of all this stuff where you have different modems that you have to use, and to fully enjoy Daniel Esteves satellites, because we think that would make our life a lot more easier at the end. Maybe with a lot of forework, but then once the system would then run, I think it would get a lot more easy. So this, for example, was using the ICAM, was an SSTV image that we, I think this one was not yesterday, but on Friday. So we get really high quality images with our antenna setup. And that is done with the SDR. So you really see that's the same path, almost same elevation, and you really see a big difference. What we also really like to do is we follow the Soyuz, and we are very lucky, because Soyuz only communicates in that region, and for the rest they don't talk at all. So as soon as they can physically have a connection with ZUB in Moscow, they start talking all the time. It's very very interesting, all in Russian, but it's really amazing for young students to hear the commander in Russian speak to Mission Control Moscow. Okay, here, that was where the first time where we really got aware about the problem that we are sitting in the second floor and our antennas are on the fifth floor. So we tried hard to get any of those tiny beacons. When we got it 1 or 2 beacons after weeks of work, and then we discovered WebSDR, a very wonderful tool. So that's a receiver. You just log on via the internet, then you connect your modem, and you finally can understand the signals coming from that tiny satellite that orbited around the moon. And then, because we really tried to get it also by our own, I discovered also this nice sheet from Daniel Esteves, and I got the idea, oh my God, maybe if we really point, it said that it does not make the difference, but maybe small difference could change the game. So then I took the book of David Valado with the students. We implemented inside of GMAT then a function that calculates, because GMAT cannot do that. That's an orbital simulation, but we needed to get the azimuth and elevation to point the antenna, and so we used this algorithm from that book, and then we wrote a program. So then the GMAT then writes down a file with all the positions. So we took the state vectors then from the Chinese guy, from the University of Harbin, or was it your you also had it on your GitHub, no? And then so this program just read it that. Okay, time is up.